For more than a century, astronomy has advanced by connecting what we see to how gravity behaves. Stars glow, gas clouds radiate, and galaxies shine, so we estimate mass from light and then check whether that mass can account for observed motion. Dark matter appears when this accounting fails in a systematic way. Across many systems, gravity looks stronger than visible matter allows. The term dark matter does not mean a substance that is metaphorically dark. It means matter that does not interact with electromagnetic radiation in ways we can directly detect. It neither emits nor reflects light at measurable levels. Yet if we remove it from our models, galaxies, clusters, and large-scale structures stop making sense. So dark matter is not a decorative idea added for drama. It is a response to repeated quantitative mismatches between observed gravitational effects and the amount of ordinary matter we can inventory. A classic clue comes from galaxy rotation curves. If most mass were concentrated in luminous central regions, orbital speeds of stars should decrease with distance, similar to outer planets moving slower around the Sun. But real galaxies often show nearly flat rotation curves. Stars far from the center keep moving at unexpectedly high speeds. That means the enclosed mass keeps increasing with radius, even where light has thinned out. The simplest interpretation is a broad, diffuse halo of unseen mass surrounding each galaxy. This halo dominates the mass budget and extends well beyond the visible disk. Importantly, this is not a one-galaxy anomaly. The pattern appears in many galaxies with different sizes and morphologies. When independent surveys keep reproducing the same mismatch, the burden shifts. Instead of asking whether one instrument made an error, researchers ask what physical ingredient repeatedly missing from the model could reconcile all those measurements. Galaxy clusters strengthen the case because they provide multiple mass probes. First, galaxy motions inside clusters indicate deep gravitational wells. Second, the hot intracluster gas reaches extreme temperatures, implying strong confinement by gravity. Third, gravitational lensing reveals how total mass bends light from background objects. These methods rely on different observables and systematics, yet converge on the same result. Visible matter alone is insufficient by a large factor. Lensing is especially important because it maps gravity directly through light deflection, independent of whether mass is luminous. In some colliding cluster systems, ordinary gas collides and slows while the dominant gravitating mass appears displaced and continues more ballistically, behavior expected if most mass is in a weakly interacting component. This spatial separation between baryonic gas and main mass peaks is difficult to reproduce with only ordinary matter and serves as one of the sharpest empirical signatures supporting dark matter. Dark matter also sits at the core of the standard cosmological framework, often called lambda-CDM. In this model, ordinary matter is only about 5% of the universe's total mass energy budget, dark matter about 26.8%, and dark energy about 68.2%. Looking only at matter, dark matter makes up roughly 85%. Those numbers are not arbitrary, they emerge from fitting many datasets simultaneously, including cosmic microwave background anisotropies and large-scale structure statistics. The key strength of lambda-CDM is cross-consistency. It does not just fit one phenomenon while failing others. It gives a coherent background where early universe conditions, growth of structure, and present-day distribution of galaxies align reasonably well. That does not mean every tension is solved. It means that removing dark matter from this framework generally worsens the global fit, making it harder to explain the universe we actually observe at multiple scales. To see why dark matter matters for cosmic architecture, go back to the early universe. After the Big Bang, matter was not perfectly uniform. Tiny density fluctuations existed. A component that does not couple strongly to radiation can begin clumping efficiently under gravity, creating potential wells before ordinary matter fully decouples from photons. In the dark matter picture, those wells become scaffolding for later galaxy formation. Over time, small clumps merge and connect into filaments and nodes, building the cosmic web. Ordinary baryonic matter then falls into those pre-shaped gravitational structures, forming stars and galaxies where conditions are favorable. This sequence helps explain how such large and complex structure emerged within cosmic time constraints. Without a dominant non-luminous gravitating component, structure growth from initial fluctuations is much harder to reconcile with observed large-scale patterns and timing. Dark matter, in that sense, is less a detail and more a structural engine. A common misunderstanding is that if dark matter dominates cosmic matter, it should dominate local environments like the solar system in obvious ways. But dominance depends on scale and concentration. Dark matter halos are extended and relatively diffuse. Locally, ordinary matter in the Sun and planets is much denser and controls nearby dynamics. Estimates suggest the total dark matter inside Neptune's orbit would be comparable to a large asteroid, tiny compared with planetary masses. So dark matter can be globally crucial yet locally subtle. This is why planetary ephemerides work without adding large dark components, while galactic and cluster dynamics demand them. The distinction between local precision gravity and large-scale gravitational budgeting is essential. Confusing those scales often leads to false objections. The same physical component can be almost negligible in one regime and indispensable in another, depending on geometry, density profiles, and the size of the system under study. Dark matter models are often categorized as hot, warm, or cold based on particle velocities in the early universe, typically described by free-streaming behavior. Hot dark matter moves rapidly and smooths out small-scale fluctuations, suppressing early small structure formation. Warm dark matter sits between extremes. Cold dark matter, moving slowly enough, preserves small-scale seeds and supports hierarchical growth where smaller structures form first and merge into larger ones. Observationally and in simulations, cold dark matter has been most successful at reproducing broad large-scale structure. That success made CDM the default in lambda CDM. However, small-scale tensions remain active research areas, including how baryonic feedback from star formation and supernovae reshapes inner halo profiles. These debates do not erase dark matter evidence, they refine its microphysics and interaction assumptions. In frontier science, a model can be broadly right while still needing adjustments in detail-rich regimes where new data exposes subtleties. What could dark matter be physically? The dominant idea is a new particle sector beyond the standard model. WIMPs became famous because many theories naturally produce weakly interacting massive particles with relic abundances near cosmologically interesting values. Axions, initially proposed for a different particle physics issue, are another major candidate and could form a cold dark matter component under the right conditions. There are also broader possibilities: sterile neutrino-like warm candidates, self-interacting dark matter frameworks, or multi-component dark sectors. A different route is compact objects such as primordial black holes formed in the early universe. But across many mass windows, observational constraints from lensing, dynamics, and background measurements limit how much of dark matter primordial black holes can represent. The field is therefore a process of elimination and synthesis. Retain candidates that satisfy gravitational, cosmological, and laboratory constraints simultaneously, while discarding those that fail combined tests. Detecting dark matter directly is difficult because its defining feature is weak non-gravitational interaction. Direct detection experiments place sensitive targets deep underground to reduce noise from cosmic rays and radioactivity, searching for tiny recoil events from rare particle interactions. Indirect searches look for excess photons, neutrinos, or charged particles that might result from dark matter annihilation or decay in astrophysical environments. Collider searches attempt to produce candidate particles in high-energy collisions, inferring them from missing momentum signatures. So far, no unambiguous discovery has emerged. But null results are scientifically productive. They carve away parameter space, improve instrument design, and sharpen theory priors. This is typical in high-precision frontier physics. The absence of confirmation in one channel does not negate astronomical evidence for missing gravitating mass. It means the allowed identity space is narrower, perhaps pointing to weaker couplings, different masses, or richer dark sector dynamics than early simple models assumed. Could modified gravity replace dark matter entirely? Proposals like MOND and relativistic extensions were motivated by real anomalies and can match specific galactic trends, especially in low acceleration regimes. That contribution is important. Alternative frameworks force mainstream models to confront detailed phenomenology rather than rely on broad claims. The challenge appears when one theory must fit everything at once. A model that reproduces certain rotation behaviors may struggle with cluster mass deficits, lensing maps, or cosmic microwave background structure. Conversely, dark matter-based models, while imperfect, currently provide better multi-scale coherence. Some researchers explore hybrid ideas where gravity is slightly modified and a dark component still exists. This reflects a healthy scientific posture: data first, ideology second. The winner is not the most elegant narrative but the framework with strongest predictive reach and cross-domain consistency. At present, modified gravity alone has not matched the full observational portfolio as successfully as dark matter-inclusive cosmology. The enduring strength of the dark matter paradigm is convergence. Independent observations using different instruments, assumptions, and physical tracers repeatedly indicate more gravitating mass than baryon supply. Galaxy kinematics, cluster thermodynamics, lensing geometry, large-scale structure statistics, and early universe anisotropy patterns all point toward the same missing component. Convergence does not prove final truth, but it sets a high bar for alternatives. Any replacement must reproduce this full network of evidence, not only one favorable subset. That is why the central question has shifted over time. The debate is increasingly less about whether a dark gravitating component exists and more about its nature, particle identity, interaction strength, possible self-interactions, and relation to broader fundamental physics. Solving that would do more than fill a gap in astronomy. It would redefine our inventory of matter, reshape particle physics priorities, and potentially reveal that most of reality is built from ingredients we are only beginning to map. If you found this helpful, please like this video and subscribe for more explainers.